and where we are heading. So we've been talking about modeling, right? We want to develop this system, identify M and K. So the first approach was for simple system. I define those as being type of problems you can easily set up a free body diagram and directly derive the equation of motion. Okay? And by deriving the equation of motion, whatever turns out to be the coefficient of the acceleration term is your equivalent mass, and this is the equivalent stiffness. But then we said there are cases that are not so easy or so simple. The system is not so simple, and in those cases you can do a variety of approaches, but all of them I sort of covered that or listed them under the umbrella of structural analysis approach. Why is that? Because these are approaches that are based on the concept, simple concept of relationship between the force and displacement. The reason is that it is the equivalent stiffness which is a more difficult element to identify or to model. And structural analysis is a technique that enables you just to do that. And these are not the kind of problems you can categorize and say, okay, if you have this, do this, if you have that, do that. But there are very clear set of tools that you have, or concepts that enables you to find the equivalent stiffness. One of them is based on the direct definition of stiffness. What is the stiffness? What is the stiffness? You should.
Okay.
Yes. What is the stiffness?
It's K.
It's K, but what is it?
The amount of force required to move it 1 unit.
Yes, so the force that generates 1 unit of displacement, right? Always remember this, F is equal to K. U, if this is 1, then the force is that stiffness. Then there are also cases, basically here the idea is you want to relate force to the displacement. Okay, find a relationship between the two. That helps you to find the stiffness. In order to do that, most of the time you can do that directly, but sometimes you need to use also concepts such as superposition, because it's not necessarily easy to find that relationship. You may remember from statics, use the concept of equivalent force systems, or you may need to use, instead of the stiffness, sometimes it's easier to use the concept of flexibility. Flexibility is the reciprocal or the inverse relationship with the stiffness. In other words, flexibility, as if the stiffness is defined, force that is required to generate 1 unit of displacement. Flexibility is the displacement generated due to unit force. You apply unit force to the system, whatever displacement results, that is the flexibility of the system. if you invert that, okay, K is the inverse of the flexibility. So you can find the stiffness of the system. As I said, there's no general rule which one to use. It really depends on the type of problem we have. So I'm gonna do a few problems to cover each one of these areas and also demonstrate that in all of these, remember, two general concepts that is very important, especially if you have system made of many components, how to add up the effect of these different stiffness components, which we describe them as the concept of springs in series, meaning springs or stiffnesses that are subjected to the same force, or they are stiffnesses that are going through the same displacement. So we call them subject to the same displacement. It's a combination of all of these that I put under the umbrella title of structural analysis. So let's do a problem which was actually a good one in your homework. So that was one of the reasons I postponed that, because I thought it's a good idea to at least cover a problem like that. Okay. Let's say you have a rigid massless bar, okay? It is supported here by a spring and another spring here, and then a spring and a mass is attached to it at this point, and you want to find the natural frequency of this system. So obviously, the first step is to find the equivalent stiffness. Mass is given, that's the only thing you have there, so it's easy. Mass is always easy, okay? So how do you do that? As this thing is going through some motion, or the rotational motion, right, theta, what happens? So if this is the original configuration, the system is displaced, you will have a force generated due to this spring, due to this spring, and then something happens here. I don't know yet. And I don't want to know yet. Let's see first what we do with this. What I do is this. I know the value of these forces that result due to these displacement. And by the way, these distances are given as L1, L2, and this length as given as L3, okay? I can find out F1 and F2, right? F of K1 is simply the stiffness of that spring times the deformation that it goes through, right? The force in this other spring is K2 times the deformation that spring goes through. But the springs that I have here, they're not either in parallel, they're not in series, right? So what do? Right? Can I use any of these approaches to solve for that problem? You remember something all of a sudden that like a sparkle comes to your mind. And that is some simple concept you had in statics. What was that?
Energy.
Summing moments.
Summing moments, no. What was the concept?
Conservation of energy.
No, we didn't cover energy in statics.
Summing.
Not couples.
Summing the forces.
Concept of equivalent systems. Do you remember that? Does anybody remember the concept of equivalent system? That was built upon the concept of couples and moments and resultant forces. What was the concept of equivalent systems? Very simple. If you had several forces spread out through a rigid body, right? You could get rid of all of them, find one single force that you can put it at any location you want, right? How do you do that? You find the resultant of all those forces, put all of those at the point you want. However, you need to add the moment, right, that results from moving these forces to there. Or in other words, the moment of this equivalent force about a point should be the same as the sum of the moment of each individual force about that same point. And we call that the concept of equivalent systems. I'm sure you remember that. You just didn't want to say that. It's Friday afternoon, you were tired. I'm proud of you. You remember those. Okay, so that's what we do. What I'm gonna do, I said, why don't I replace these two crazy forces and put them, okay, put a force F3, which is equivalent to the action of these two, right? But is acting at that point. So in order to do that, you need to have the moment of this force about this point A, right? In other words, times F3 should be equal to the F of K1 times L1 plus F of K2 times L2, right? That's where you find this force, this unknown force, that can replace all of these forces. So that's what I would do. F3 times L3 then is K1 L1 theta times L1, right, plus K2 L2 theta times L2, okay? So F3 then, right, would be K1 L1 squared theta plus F2 K2 times, I'm sorry, I have F2, okay? Okay, because I wrote, this is my own handwriting and I cannot read it, right? Okay, divided by L3. But let's assume that this F3 is actually, since it is moving in this direction, and that's where the direction of the motion is basically taking place, is a linear motion, let's assume this F3 is the result of a spring, which I call that, whatever, spring K prime, that has resulted in that force. So if that's the case, this K prime is going through a deformation, right? That is K prime times L3 theta, right? That is that force, okay? So therefore, K prime L3 theta is equal to K1 L1 squared plus K2 L2 squared divided by L3 theta. Thetas cancel out, so we found K prime would be K1 L1 squared plus K2 L2 squared divided by L3 squared. So I found the spring that I just put this there, and that spring acts as a replacement for these two springs. That's what I reduced the problem to. And of course, don't forget that we still have this spring that for the time being, we had just set them aside and attached to this beam. So now the problem becomes very simple. We have two springs attached at this point. This is just a rigid bar, so no mass, nothing. So this acts just like a connection between these two. So would these two springs be in series or parallel? do they experience the same force or the same displacement? The same force, right? So these two are in series, so therefore the K equivalent then would be 1 over K prime, which we found, right, plus 1 over, or in other words, 1 over K equivalent plus 1 over K3. So that will give me K equivalent, and therefore the natural frequency would be that K equivalent over M. So the point is that you see that this concept of structural analysis is just based on general concept and understanding these basic knowledge from statics or strength of material. So that's one example. Any questions? Let's look at another interesting problem, and actually two more interesting problems, before I introduce yet another interesting problem. How about that? So the one I'm going to briefly go over like this one is in fact also a problem from your book, understanding of which I guess gives you a good competency in understanding the concept of springs in series or parallel. Okay. So this is this famous problem. I kind of glanced through this maybe here, but then I realized it may not be a bad idea to go through that in more detail. Did you have any difficulty doing this problem?
I think you covered this question last lecture.
I did, I guess, right? Did I
Yeah.
give you thoroughly go through that?
No, yeah.
I didn't. So who thinks that I did? And who thinks I did not? So it's half and half, so I better go. Okay. So you have a disk subjected to some rotation. On one end, 3 shafts are attached to it. On the other one, a single shaft, and then these 2 linear springs. Radius of this is R, and we want to find the equivalent stiffness for this system, okay? As you imagine, if you subjected this to a torch, right? What can you say about the force in these 3? Can you say that these 3 experience the same force, or they go through the same deformation? Same force. You don't know how much each would be for, because the stiffness of each one is different. So, therefore, if these 3 are subjected to the same force, you can replace that with a single stiffness. They're in series, so you can find that single stiffness from this relationship, right? So then the problem is reduced down to this. So you have this K prime, you have this K4, right? And of course you have these 2 springs. Now, if I rotate this mass, are these in series or are in parallel? Are they subjected to the same force or they experience the same deformation? I cannot say anything about the force. How do I know? How much is the force here and here? But I know they are constrained, and if I turn this, both of them experience the same deformation. Therefore, I can replace this and that with another equivalent spring, which would be then sum of these two, right? So now I have a single torsional, basically spring, and two linear springs that are attached to it. How do I convert those linear springs to torsional spring equivalent? First of all, these two experience the same deformation. As this turns, this would go through a turn of, say, theta. So this would be this distance that these two experience, the displacement that these two experience would be r theta, right? Both experience the same deformation, right? Yes?
Would you mind briefly explaining why K4 and K prime are in parallel?
They're in parallel because they are experiencing the same displacement. You cannot say they are experiencing the same force, but you can say, any other questions? So if these are experiencing also the same displacement, that means K5 and K6, although they're positioned in a crazy orientation, they're in parallel. So K5 and K6 then can be replaced by a single linear spring that is that. By the way, these are all torsional springs. So I better put this KT here. But that one is a linear spring. But these linear springs, right, how they can be converted, their effect, to a torsional spring? They are acting, in other words, they're generating this thing, or is subjected to generating a force F. That force F would be K triple prime times the displacement that this goes through, which is R theta. And with respect to the center of the shaft, okay, this force generates a moment of F times R, which would be then K triple prime R squared theta. Okay? So this is the corresponding torsional spring that some of these two springs generate, and these are in parallel with the original spring, so the total, I call that total spring, then would be this K triple prime T plus, okay, what did I call that? Yeah, K triple prime T plus K double prime T, right? Of course, these are going to be some messy fractions, long terms and whatnot, but that's the concept. Any questions? Okay, so with that said, I'm going to yet do another problem here. Okay. Two more problems. Okay. So let's show do a problem that shows the concept of superposition. Let's look at this example. Let's say you have a mass rigidly connected to two beams, and this moves back and forth. Since the connection between the beams and the mass is rigid, as this moves, the movement or the shape of deformation would be like this. In other words, you have a rigid connection here, that means as if internally there's a force and a moment that has caused that kind of deformation. Or in other words, if you look at each of these beams, it is as if you've had a force and a moment that has resulted in that deformation, okay? So in order to find this displacement, which is what we need to find the stiffness of this structure based on the direct definition of a stiffness. Force that generates a unit displacement is the stiffness. So if I can relate the force in the direction of the displacement to this displacement, set that equal to 1, the force would be the stiffness. How do I do that? I would superimpose these two. In other words, I would look at the effect of this load and this moment separately. This force causes, this is, you remember, cantilever beam, causes a displacement, I call that delta 1, and a rotation that I call that delta theta 1. This one generates a displacement, I call that delta 2, and a rotation, theta 2. I know that since no rotation takes place here, theta 1 plus theta 2 is equal to 0, and delta 1 plus delta 2 is the displacement that I want to find, because that is related to the applied load, and I can use the concept of the stiffness to find the stiffness equivalent to stiffness. From strength of materials, you know delta 1 is PL cubed over 3EI. And theta 1 is, okay, PL squared over 2EI. Okay, and the delta 2 is minus ML squared over 2EI, and theta 2 is minus ML over EI, okay? Knowing that theta 1 plus theta 2 is equal to 0, if you substitute those into this equation and equate that to 0, you will see that M comes out to be PL over 2. Therefore, I can substitute that in this, okay, delta 1 plus delta 2, which is PL cubed over 3EI minus, substitute for M, which is PL over 2 times L2 over 2EI. You see that this, which is delta, would become PL cubed over 12EI. So if this is 1, this is the stiffness of that beam or column, therefore K is 12EI over L cubed. So for this system, which consists of these two beams that they experience the same deformation, right? They are in parallel, they go through the same deformation, so the total, the stiffness of a system like that would be 12EI over L cubed plus 12EI over L cubed, so it would be 24EI over L cubed. Concept of superposition. So that's another thing that you may want to remember. As I said, this structural analysis is a very broad approach. You can utilize all your knowledge from statics and the strength of material to just try to relate the stiffness to displacement. That's the objective. In this approach, you try to relate the stiffness to displacement. So you use all those methods, but also remember the concept of series and parallel to spring summation. Okay. So I promised to do another interesting problem, right? So let's do it. Any questions? Okay. So this concept of structure analysis is very interesting. You can do all kinds of interesting problems just by using those basic, simple definition or concepts. So this is a good example. Let's say you have a disk which is massless, can pivot about this support. A spring with stiffness K is attached to it at some point distance A from the center of this disk. This is, as I said, massless. And then at this point, you have attached a cable, an inextensible cable. In other words, cannot be stretched, cannot be deformed, anything. And then you have connected a mass M to it. So you want to find this equivalent system. And a key component of that is this. This is easy, you already have it. This is massless, so the only mass in the system is this guy. And that is the one that is moving up and down. Okay, so how do you do that? Well, just thinking about all the concept, series, I don't have two springs here that are in series or in parallel, so forget about that. Superposition, useless. The only thing that really helps me, going back to the basic concept of the stiffness. But even that, you said stiffness is the force that causes what? A unit displacement. That doesn't do me any good. However, I remember the concept of flexibility, which is the inverse of the stiffness. What is flexibility? Flexibility is what? Anybody remember flexibility? What is flexibility? Anyone? Stiffness is the force causing a unit displacement, right? Flexibility is the displacement due to a unit force. So if I can apply a unit force along the direction of motion to that mass, right? And then measure the displacement that is generated as a result of that unit force, that displacement that I will measure would be the flexibility. So if I find that flexibility, then the stiffness would be simply 1 over that flexibility, and that's it, that's all I need. So how do I do that? So I would assume I have a unit force applied here. But since this is inextensible, if I apply a unit force here, it is the same as if I have applied a unit force here, right? Doesn't matter, it's the same. Okay? So as a result of this, let's say this disk is going to rotate. Let's call that angle rotation theta. So this point A goes to point A prime. A prime is delta A. This is the flexibility that I'm trying to measure, because it's a deformation, displacement due to the unit force. But this force, this point B is also going to go to a point B prime, and this distance, since this angle would also be phi of A, right? So this distance delta would be what? Would be A times phi of A, right? So the force that is generated in this spring, force would be K times A times phi of A, right? But now let's look at the free body diagram here. Free body diagram is a good thing. Don't forget the power of free body diagram. What do you have here? It's a massless disk, so that's useless, right? So all I have is this force, one unit force, and this is R0, this is at A, right? And then I have these two little guys here. This is point O, right? So I can take summation of moments at O is equal to 0. So I have 1 times R0 is equal to A times Fk. Fk is this guy, so it would be K A squared phi A. So I get this relationship, right? But that's not what I want. I want this guy, right? Right? And what is this guy? Delta A is R naught times phi of A, right? What is phi of A from here? Phi of A is R naught divided by K A squared, right? Therefore, delta A, which is what I want, is what? Is R squared divided by K A squared, right? What did I say? I said delta A is what? What was delta A? I think you are so tired, cannot wait for the weekend, right? So what is delta A? Flexibility. And flexibility is the inverse of the stiffness. So the stiffness of the system is 1 over delta A. Okay. So you can see the power of structural analysis approach, which is a very simple, no concept that you can say that you've not had that. You've had statics, you've had the strength of materials, and you know the concept of springs in parallel, springs in series. So with a little bit of thinking, if you're given a problem, that the essence of that is to find the equivalent, the stiffness in the system, you can use those, find the equivalent stiffness, and then having just one mass element which moves in a single direction, you can find the equivalent system. In other words, that ugly looking system, in terms of the vibratory motion, is nothing but this little nice looking single degree of freedom system. Okay. So with that said, we have covered two approaches as far as the equivalent systems or finding how to find the equivalent stiffness and mass in a system. We have 2 minutes, so at least I can give you a preface to the next topic. How about that? So you get so excited over the weekend, you can't wait for Monday. That you come to them, okay? So we talked about 2 approaches, and I promised you we will have we discussed 4 approaches for modeling a system and in terms of a single degree of freedom system. The first approach was simple, I call that simple systems. How about that? Remember, free body diagram, equation of motion. That was the approach. The second approach, we call that structural analysis, which was based on the definition of the stiffness or flexibility using the concepts of superposition and the concept of parallel plus series springs. The third approach is energy methods. You've had this in dynamics, I'm sure you have. Except that here is a little bit different because in dynamics you are only dealing with rigid body systems. So what we will do here, we use the concept of the what? Conservation of energy. Sum of kinetic and potential energy is always constant, so that sum doesn't change with respect to time, so the derivative of that constant value is always 0. That's basically it. And then we get into a little bit more advanced energy method, like Lagrange's approach, and then Rayleigh's method. These are the 3 areas we cover, and then we are ready to go to study the response of the single degree of freedom system that we have modeled. Have a great weekend.